Okay, good morning again. As I said, we are going to finish Poisson distribution today, and we are going to start chapter 4, which is continuous discrete continuous distributions. Some of those are still related to some of those continuous distributions are related to the discrete distributions we have seen and we are going to see. Like exponential distribution is closely related to Poisson distribution, and the parameter that we're going to see this lambda has the same meaning in both Poisson and the exponential distribution. The average number of events that occur in a fixed time interval. That's the lambda parameter. Frequency or average number of events, you can think about that. And if, for example, the number of events that occur in a fixed time interval is lambda, the average waiting time for a single event is going to be 1 over lambda. So this is how they are related. So we are going to use exponential distribution to model waiting times. And in that case, the waiting time between two rare events will be 1 over lambda. So this is how they are related. All right, so, but if Poisson distribution is about the number of events that occur. So it's discrete. So when we are counting things with like these integer counts, it may be the number of trials, it may be the number of successes. In this case, we don't have the parameter p. We are not doing trials, Bernoulli trials with success probabilities. We are just observing events that as they occur around us. So this is what Poisson distribution is about. For example, you're observing how many cars are coming to this gas station every hour. So that's, for example, can be modeled as a Poisson distribution. Number of accidents that occur in a day. Number of rainy days in a month in Ankara, number of rainy days in a month in Trabzon. So these different events, number of certain events in a fixed amount of time. Usually this, whether in a year or in a month, should be specified in the variable's description. So when you're specifying lambda, you say this is the number of things that occur in that time interval. So it has to be given. So with that parameter, its probability mass function, which is actually written as fxx, right, like this, is given as e to the minus lambda to the power x divided by x factorial. This is just, we are not going to talk about the derivation of this. We just assume this is how they are. This is what the probability mass function gives us. For example, the probability of observing 0 events is going to be e to the minus lambda to the power 0 divided by 0 factorial. So in that fixed specified interval, for example, if 5 cars arrive at this gas station every hour, it's probable that no cars arrive at the next hour, or it's probable that 20 cars arrive at the gas station in the next hour. So these are all probable. It's the variable x, its domain is again ranging from 0 to infinity. Okay, we can observe 0 cars. On the average, the fact that 5 cars arrive at the gas station on the average in an hour does not exclude the probability that no cars are going to arrive in the next hour. So still observing 0 cars has some probability. So fx 0, observing 0 cars in the next hour is going to be e to the minus lambda to the power 0, which is 1, divided by 0 factorial, which is also 1. So this e to the minus lambda is the probability to observe 0 cars in the next hour. Okay, so it's expected value, since we are given the average number of cars already, average number of events that occurred in that time interval already as lambda. So our expected value is the parameter of this distribution, which is lambda. Let me also change the mouse size. It's not. I click on the thing. Mouse, yeah, mouse size. So let me make it 4. All right. So yeah, this is it's expected value is lambda, and its variance also is lambda if you try to solve the infinite series. Again, x, we're going to sum for all possible values of x from 0 to infinity. We are going to sum this geometric series, which is e to the minus lambda to the power x, and x factorial. X is from 0 to infinity. If you multiply it with x, you find and sum. If you multiply it with x and sum it with from 0 to infinity, you get the expected value of x. Then you find the expected value of x squared by multiplying this with x squared and find a summation. And if you find the difference of the expected value of x squared subtracted, and you subtract from it the square of the expected value, you again get lambda. So both the expected value and the variance of Poisson distribution is lambda. Now let's take a look at an example. The one thing that we need to be careful when we are solving Poisson-related problems is that we are going to see that thing we are going to be careful in this example. So I don't want to just spoil the example now. So let's go ahead and take a look at this example 3.22. Okay, so all these how the summation from 0 to infinity gives us lambda, how the expected value of x squared, this one gives the variance. Actually, yeah, this one gives us the variance. Okay, so here is example 3.22. New accounts. The part B is an interesting problem, and that we want to be careful about when we are solving Poisson-related problems. So here is we are given customers of an internet service provider initiate new accounts at the average rate of 10 accounts per day. So this is our lambda, and lambda is given here to us as per day. So it has a time unit, which is a single day. Every day we get 10 accounts on the average. That's our lambda. If we're asked a question, the thing that we need to be careful about is that when we're asked to a probability saying that what is the probability that 16 account will be initiated within 2 days, we cannot just write this random variable as the summation of the two previous variables. It's not if the random variable that the average number of accounts per day is random variable x, this other variable is not x plus x. All right. So the probability we cannot. What is the because it's not independent when you're doing the things. For example, the fact that you observe, for example, 5 accounts in the first day, then you have to observe 11 accounts in the other day. You cannot just sum those probabilities, because to get the probability more than 16 accounts per day, there are many possibilities that you can arrive at that 16. So the thing that we need to be careful about is that when the time frame is extended or shrink to a different amount than the one given in the question, we need to treat it as a separate Poisson variable with 2 times lambda, whatever. For example, this is 2 days. It was given lambda is equal to 10 here. This is going to be another Poisson variable with lambda is equal to 20. All right, but so when we are solving the probability, we need to look at a different table with a different lambda parameter. In this case, lambda is going to be doubled. For example, if you observe 10 accounts average per day, obviously in 2 days your average observation is going to be 20, right? In a week, for example, in this company, how many average rate of accounts, I mean, assuming that weekdays and weekends are equally likely, when somebody asks you what is the average number of accounts per week, we will immediately say that it's 70, because there are 7 days a week. So our lambda is going to be 70. So what I'm saying is that the thing that we need to be careful about is that when we're asked the probability about this internet service provider about that happens in a week, we need to treat it as a different Poisson variable in which the lambda is modified to account for this time change. We cannot just try to compute the probability by just adding the probability or adding the things we have found per day. Okay, so this is actually also indicated here. Actually, yeah, what I was trying to say is written here. The number of accounts Y opened in 2 days does not equal 2x. It's not x plus x. It's a different, this random variable is not a summation of variables. What I'm trying to say is it's not the Poisson, when the time is extended, it's not like a generalization of negative binomial to geometric or binomial to Bernoulli. All right, when we have multiple trials. Here, these 2x days is not multiple trials. It's the period is extended, but those events can be spread throughout those 2 days in different places. We cannot just divide 8 of them are going to happen in the first day, 8 of them are going to happen in the second day. For part B, we are looking for 16 accounts. So we cannot just say 8 and 8. They could have been 1 and 15, 0 and 16. All these different things could be possible. So in order to account for these different probabilities, we shouldn't just treat it as a summation of 2 random variables. Rather, it's another Poisson random variable whose parameter now equals 2 times lambda. Okay, so this is the important thing that we need to be careful about when we are solving Poisson-related problems. So what is the probability that more than 8 accounts will be initiated today? We can actually, the probability that x is going to be greater than 8, what we can do is, since this is more than 8 accounts, the complement of this event is what is the probability that 8 or less accounts are going to be initiated today? Because if you're asked the probability more than 8, which means that 9 and onwards. What is the probability that 9, 10, 11, 12, or infinity number of accounts are initiated today? We look at the complement event. What is the probability that 8 or less accounts are initiated today? That's our cumulative distribution function. Yeah, the most possible is 10 accounts, exactly. That's like on the average, we arrive 10 accounts, and 9 accounts and 11 maybe equal or maybe not equal. We don't know. Maybe 9 accounts is it more is it going to be? Yeah, I think they're going to be equal because like after 9 accounts. But yeah, we need to look at the distribution too. But that's a good point. The graph of it doesn't look like a normal distribution, but it will be when this if you try to look at the PMF, the graph of this Poisson distribution, it may look like so 0 is, so it's not going to be like normal distribution centered at something. Okay, we can actually try that PMF and try to see, try to write this and fill in MATLAB, or we can just, let me just try and go in and Google it. PMF of Poisson. So we can, so it's for certain values of lambda, it's going to look like for large values of 10, for example, when lambda is equal to 10, it indeed looks like the normal distribution like this for lambda is equal to 10. But for lambda is equal to 4, for example, as you can see, it's right skewed. We know that it ends at 0. It doesn't extend to the left of 0. It will start at 0. And most of the time with non-zero probability at 0. And depending on what lambda is, it's going to look like a normal distribution with some, so it's going to be centered around something like this. So for 10, for example, when lambda is equal to 10, we have something that looks like this. I mean, if my finger is pointing exactly at 10 right now, you can see that 9 and 11, they don't have the same probability. Okay, so it's not exactly 10 is not exactly the center because it has a tail all the way to infinity. Its tail does not go below zero. So it's not, we cannot say it's like normal distribution. We are going to talk about, we haven't seen normal distribution yet, of course, but in normal distribution, both tails are symmetric and both extend to from minus infinity and to negative to positive infinity. Here in Poisson, we don't have that. Oh, so let me also go to the your last question, which is how did they find in part A? How did it find that 0.333? So this one. This is, we look at the table. So here, either we can use MATLAB to query for the Poisson CDF. For example, probably if we do that, Octave Online, let's go to Octave Online, and we need to, it was Bino CDF, right? Bino CDF for binomial. So I just want to figure out which package I need to load. Yeah, this one, package load statistics. So I need to type this one all the time. So probably we also have Poisson CDF, undefined. Oh, so let's see. Let's go ahead and search again. Google, what is the Poisson CDF? CDF MATLAB. Its name is yeah. They just made it shorter by removing two characters. So just Poisson, not Poisson. I don't know why they did that. So they get X and lambda. So the two characters are taken out. So it's like this, plus CDF. For example, the probability to obtain 9 when the lambda is equal to the probability to obtain 10 when lambda is equal to 10 is this. The probability to obtain 9 when the average is this, and if you look at, for example, 11. Oh, these are no. This is CDF, not PDF. So we can actually take a look at the PDF to see what those probabilities, individual probabilities are. So this is what we're looking at is the PMF. So if you look at this, what is interesting is that the average was 10, right? 9 and 11 are not the same probability. 10 and 9 have exactly the same probability. It seems like 10, and although the expected value is 10, 9 also has a very, up to 4. I don't know whether they will differ after this certain decimal points, but the probability to observe 9 events when the average number of events is 10 seems to be equal to that the probability to observe 9 events is equal to the probability of observing 10 events when the average number of events in that time interval is 10. And it gets reduced like this. So if you look at the CDF of 8, this is how we obtained 0.33. Okay, so this is the cumulative distribution function, the part that I highlight here, shows the probability of observing 0, 1, 2, 3, 4, 5, 6, 7, 8 events in this time interval where the average number of event occurrences 10 per day. So the probability that 8 or less customers are going to open new account is equal to 0.33. So 1 minus that, the complement of this will be the event that the probability of 9 or more customers initiate an account that day. So when we try to solve the probability for 2 days, what is the probability that the Poisson doesn't work? A good question. Will it work if we know the minimum and maximum occurrences too? Usually it doesn't work. So we're just given the parameter, the average number of occurrences. We have to use a different distribution if we want to limit the minimum and the maximum. So another good question, when we are solving these problems, which distribution are we going to use? you have to actually get a feeling of what those distributions mean. Actually, there may be some questions in the midterm that ask you exactly what you have asked. For example, in this question, we are going to pose a question and tell you that what kind of a distribution is most suitable to model the probability, the random variable in this question. In order to figure out which distribution is most suitable, you need to know what these distributions mean and what they are used for. For example, if you're given a parameter that says the number of average things that occur in a certain amount of fixed time, that's immediately the lambda parameter. Or if you're wondering about, for example, I want to do certain number of trials, I'm tossing coins, or I'm doing these things, and I want to continue tossing coins until I get 9 heads. For example, in that, it's going to be binomial. The number of successes, it's not binomial actually, it's going to be negative binomial, right? Because in that case, you fix the number of successes to 9, and you're wondering about what the number of trials are. So each of these distributions, they have certain semantics behind them, and they are used for certain types of problems. But when you're faced with a really completely new problem, so in the exam, we are going to ask questions to you, pose these problems in such a way that these families of distributions that we have seen in class are going to be sufficient to model the problem at hand. But your question, for example, in general, for example, when we are faced with a new problem in our research, how do you figure out which distribution it is, how we are going to model that? In some cases, there is no distribution that fits your observed data. Sometimes what you do is you just observe, you collect data, you look at the histogram, and you check whether this histogram looks like the PMF or the PDF of some distribution you already know. For example, one thing that researchers were misled was sometimes they think many distributions look like normal, although they may not exactly be normal. One example is in bioinformatics, for example, when they were doing sequence alignment and looking at alignment scores. They thought that when they looked at the scores of aligning random sequences, the scores were average around some value, and they were decreasing on both sides. The histogram was like a bell-shaped curve, and they immediately thought that this should be normal distribution. But at the end, they figured out that distribution, actually, when they perform more experiments and collect more data, they figured out that the distribution is not symmetric. Actually, it's skewed towards right. It has a more heavier right tail, so normal distribution is not suitable for that. And they then decided, oh, there's another distribution. I mean, this distribution we are not going to see it in class, but it's called the extreme value Gumbel distribution, and it fitted better to those observations. So you just look at the literature, see whether there are distributions that fits your data, or if you already know the semantics of what your random variable is, there may be what we are seeing in this course, those families of distributions, they cover a wide range of real life phenomena. So one of them is going to probably be okay. If you have, for example, large numbers and you're taking sums, it will be normal distributions. We are going to see that there's the central limit theorem, which states that the summation of random variables, for example, if you're interested in summation or averages, whatever the underlying individual random variables distribution is, independent of what the individual random variables are. Individually, they may be some arbitrary thing, exponential. But if you look at their sums over large numbers, it always is normally distributed. The summation is always normally distributed. This is called the central limit theorem, and we are going to see that today or next week as the time permits. But this is in chapter 4, and most of the things, therefore, will be normal distribution, will be very useful to model things that are averaged or summed over large quantities. Um, times, waiting times will be exponential most of the time. Certain commodities, electricity you spend, the weight of certain things, for example, gamma distribution we are going to see in chapter 4 is going to be suitable to describe those things. So as I said, many real life observations will be able to model with the distributions that we see in this course. So we will really cover a wide range of those. But still, there may be things that are not suitable. There may be distributions, and we're also going to see that. There may be this multimodal distributions or distributions with arbitrary PDFs. For example, if we have a distribution that looks something like this, okay? If you look at the data and you see that this is the histogram, okay? So what distribution is that? There is no family of distribution with these four modes, four peaks that you see here. Okay, so what kind of a distribution is this? This is not gamma, Poisson, exponential. So in this case, we're also going to see techniques to have an arbitrary PDF like this, probability density function, and we'll be able to generate random numbers. In chapter 5, we are going to see towards the end of the semester, we are going to learn techniques to generate random numbers from this distribution. Okay, for example, if you want to say this may be some distribution that you're going to use in a simulation or a computer game. These may be, for example, the number of avatars that you spawn every minute, and you want to just make it run random, and by chance you may get this number of avatars or this number, so that are spawned, for example, again in an hour or a minute. So if you want to generate this as a random variable from this PDF, we'll see that there are methods that just by using a uniform number generator between 0 and 1, we will be using uniform random numbers. By using those uniform random numbers, we'll be able to actually generate from this random variables that follow this distribution. What does that mean? It means that if you generate 10 million or 100 million random variables with this technique, and when you look at the histogram of these 10 million numbers you just generated, the histogram is going to look like this. So we'll be able to generate numbers from arbitrary distributions. So we'll also learn that. But in general, when you're faced with a problem, you need to know the semantics of these distributions, what they mean. Rare events occurring in a certain amount of time, the average number of events, that's Poisson. Waiting time between two rare events, that's exponential. Or number of trials until first success, that's geometric. Number of trials until decade success, that's negative binomial. So you need to really digest these and understand the semantics of these distributions to decide which distribution you are going to use in what question. So that's basically you'll get used to by after solving lots of exercises and problems. All right. So if you look at this example, we make use of the CDF from at the end of the book, the appendix, table A3. To get this 0.333. You may also use MATLAB or Octave Online to get this probability. So after in the exam, you'll probably mostly leave it like this. If you ask a question like this in the exam, you're not going to give you the table, for example, and leaving the solution as such will be sufficient, because this one is just a table lookup. I mean, after you get your solution until this point, 1 minus fx8, which means that you have solved the problem. This is just a table lookup or some function call in Octave Online or MATLAB. This will be your solution that you're going to write in the exam. Or maybe we'll allow you to use Octave Online in the exam. That may also be the case, because I think we are going to randomize some of the questions. Therefore, in order to grade them, like with this black box grading of individual questions, we will require you, just like the quizzes, we will require you to enter numerical values as your solution. And for that, you may just like allowing calculators in class, we are going to allow you to use Octave Online. So you will have access to these infinite tables for Poisson, all these cumulative distributions, you will have access to those. We may also provide those function names. If you're going to allow you to use Octave Online, we can give you a reference look saying that, okay, this is the Poisson CDF, this is how you use it, this is the binomial CDF, this is how you use it. So don't worry about it. You don't need to memorize any function names. All right, so to solve for the problem of 16, as I said, we need to treat it as a different variable. So this one, this time, we need to ask this question. Poisson CDF 16, not 16, what is the probability of obtaining more than 16 accounts? And 20. So we are going to take a look at this, and 1 minus that is going to be what you're looking for, right? Yeah, 1 minus that, 2 to 1 is going to be our result. So yeah, this is one thing that you should be careful about Poisson. There's also, when you looked at Poisson, when lambda is large, in other words, when we have small probabilities and a large n, we can actually approximate binomial problems with Poisson. When the number of trials is too large and the success probability is small, like this, we can say in this number of trials, the average number of successes is n times p. We know that the expected value of binomial is n times p. If n times p is something reasonable in this lambda, if n is large and p is small, usually these are, you may use this 30 and this p success probability of 0.05 as thresholds, but if it's 0.07, can I still use it? Yes, you may still use it. If it's 29, you may still use it, or 25, you may still use as an approximation, because it will not give the exact probability, but it will approximate the probability you're looking for very closely as this number gets large and this one gets smaller. So if you look at example 325 in the book, which is the birthday problem, so let's see what the birthday problem is. So here, yeah, Poisson binomial with parameters the number of trials n and the success probability p can be approximated with a Poisson distribution. You may define a new random variable with the expected value lambda to be n times p. So mathematically, it means the closeness of this thing, the limit of as n goes to infinity, as p goes to 0, and np goes to n times p is close to lambda. Their limit of this function is going to be this. So this is actually how the PMF probably is driven. So this is what Poisson has shown when he came up with this distribution. When P is large, we can still use the Poisson approximation by taking the complement of this. In case we are going to model the number of failures as a Poisson distribution. So let's take a look at this birthday problem. There's another example that uses this binomial approximation to Poisson approximation to binomial, but let's take a look at this birthday problem. Actually, it's a continuation of some exercise on page 36. We can also refer to that, but let's read the example here. Consider a class with more than 10 students. Compute the probability that at least 2 of them have their birthdays on the same day. How many students should be in class in order to have this probability above 0.5? So there's also an interesting question. The probability is given to us, and we are asked a number. The probability is given. It's not the success probability or anything. So the result is given to us. So we're also asked to solve an inverse problem. Poisson approximation will be used for the number of shared birthdays among. So if there are more than n students, n choose 2 is the number of pairs of students. So this is the number of trials we are going to do. We are going to select 2 students. The probability that a pair of students have their birthdays on the same day is actually 1 over 365. Okay, if you just select 2 random students, whatever the birthday of the first student is, the probability that the second student is going to have that same birthday is 1 over 365. So this is our success probability, which is really small, less than 0.05. And when we have more than 10 students, this n choose 2 is going to be a large number. For example, when we have 10, it's going to be 10 times 9, which is 90 divided by 2, 45. So we will try 45 pairs of students with the success probability of each trial 1 over 365. Now, here each pair is a Bernoulli trial, either they match or don't match. And besides, matches in 2 different pairs are nearly independent. We can think about that. And therefore, the number of pairs having sharing birthdays is almost binomial with n greater than 45 in this case. The n choose 2, this for the case of n is equal to 10, is going to be 45. So we use the Poisson approximation with roughly n times p, which is going to be this number. If you multiply the number of trials multiplied by 1 over 365 is this one. So this is our Poisson random variable. So the probability that we're asked 2 things. What is the probability that at least 2 of them have their birthdays on the same day? By the way, this is the probability that there are 2 students sharing a birthday is the probability that there are no matches. What is the probability of no success at all? What is the probability of 0 events in that and trials is the probability of, so this is x is now our Poisson random variable. X is equal to 0. We don't observe any rare event. That rare event being sharing of a birthday. The probability of observing no rare event will be equal to this roughly minus, and this approximation is again negative Poisson approximation of the binomial. If you just plug into this PMF where and you plug in x is equal to 0, the right hand side part is going to be 1 and divided by 0 factorial e to the x, which is 0, divided by x factorial, which is 1. Sorry, both of them are going to be 1, and therefore it's going to be this formula. And if you plug in what your lambda is right here, and square divided by 300, roughly. So we again approximate this again by n square minus n could be approximated roughly by n square. So this is what we get at the end. So when we solve the equality, in order to have this probability greater than 0.5, we have to solve this inequality to find n greater than 22.5. In other words, in a class of at least 23 students, we have more than 50% chance that at least 2 students are going to share the same birthday. Okay, so we first find the probability in terms of n as a generic probability, and then in order for this probability to be greater than 0.5, we just solve this for the only unknown n in this problem to solve for n. Yeah, we can also try this in chat. Whether we can. So there are 49 students right now in this class. Obviously, they will share a birthday. But when we ask what is the probability that somebody has birthday today, that's a different problem. We will not be trying that. For example, today is 8th of April. Again, the probability to have birthday today is 1 over 365 for a single student. Okay, the probability that they have their birthday April 8 is there, and we're not trying this time it in and choose 2 like this because we're not comparing 2 students. In this case, if we try to model this, Actually, we can still model this with the Poisson approximation. Now, this time we have 49 participants. 49 participants, that's our n, this time is 49, not n squared. N is equal to 49. And P is again 1 over 365. We can use to find it, what is the probability, for example, to have at least one person to have a birthday today, April 8th. But we will have a lot more probability to have a shared birthday. But it will take, I mean, all 49 of you have to write their birthdays in the chat and then compare birthdays. So we have to do and choose two comparison to see any two of them are equal, right? Or, I mean, you can just put it in, sort them and see whether they're two of them come right after each. All right, so that's what Poisson is. All right, so yeah, it's a really, we can also try, for example, compute the probability to, for example, for 49 participants. What is that probability? Just plug in 49 here, and to compute this probability to have at least one pair of students. So this 1 minus this probability will be the probably it will be. So if you just plug in here, instead of n squared, plug in 49, and instead of 1 over 730, just plug in 1 over 365. You can compute this probability, and it will give you the probability that two students share the same birthday today in this synchronous class. Yeah, so, all right, actually we can even do that directly on Octave Online, right? So what is the Poisson PDF with 0, 49 times 1 over 365. This is what we have, right? N times P. So yeah, it's close to 87%. So the probability to have, 0 is it's actually, it turned out to be, did I do something wrong here? No, maybe 49 is a small probability. When you multiply these two things, it may still be small. So the number of times we're trying is not that large. So actually, so this is the probability that none of you shares. Actually, I did it incorrectly. You're not, I'm right now, this is the probability that none of you have April 8th as our birthday. So the probability to have one of you in this class have the birthday of April 8th is 1 minus 0.87. Okay, so it's still, we have like around 10% probability. So what we have to do is, in order to solve whether two of you share the birthday, we need to do this, 49 times 49 on the average. So this is roughly divided by 730. So we have to look at this one. Yeah, it's going to be close to what Hassan found actually, which is 0.96. So with very large probability, with 0.96 probability, two of you in this class share actually birthdays. All right. So n times p is the lambda. So here the Poisson part is n is the number of trials, p is the success probability. The average number of successes in those trials is we use it as our lambda. That's why we are using n times p. N times p is not the probability, because if you multiply, for example, if the probability that an event occurs is p is 0.2, if n is 100, 100 times 0.2 makes 20. So 20 cannot be a probability, it's lambda, the average number of successes in 100 trials. Okay, so n times p is actually the average number, just like in binomial. What is the meaning of binomial? In n trials, what is the average number of successes if an individual success probability is 0.2? For example, if p is 0.2, n is 100, in this case, the average number of successes is going to be 20, and that's going to be our lambda. If you do 100 trials, if your 100 trials is like a fixed interval time, you will observe 20 successes on the average in every 100 trials. So therefore, our lambda becomes that 20, which is not the probability. Okay? So this is how they're related. So it's average number of events. These, in this case, the events are our successes in fixed number of trials becomes our fixed amount of time. If you, for example, do the trials every minute, okay, then the time is like every 100 minutes, we see 20 successes. That becomes the Poisson random variable. Yeah, it's really with very high probability. 1 minus this probability, two of you share the same birthday, which is probably not today. All right. And the probability that one of you have a birthday of April 8th is also not that small. It is this probability with 0.12 or rounded to 13, with 0.13 probability, one of you have a birthday today. So that concludes our chapter discussion on chapter 3. And now we're going to move on to chapter 4, which I will just do a small introduction in the next 3 minutes, then we are going to have a break. So these are the things that we're going to see. We are going to revisit the discussion on probability density. We already talked about this actually, probability density functions and its relation to PMF. So I may quickly go over this part. Then we will see 4 distributions, the 4 families of distributions for continuous case. The first one, uniform distribution, which is used a lot. All your random number generators that you use in C, Python, they usually give you uniform numbers. Actually, they are pseudo-random number generators, but they give you uniform values between 0 and 1 most of the time. I think in C, for example, it doesn't give you any real number. It gives you an integer between 0 and max int or 0 and 2. So in different cases, this rand function in different languages work differently, but most of the time they give you uniformly distributed values. And most of the time, between 0 and 1, real numbers between 0 and 1, each of those numbers being equally likely. This is what we call uniform distribution. And there is also exponential distribution, gamma distribution. Exponential is very related to Poisson. Exponential will be used to model the waiting time between 2 events. And it's also similar to exponential, is like a continuous case of geometric distribution. If you remember what geometric distribution was, geometric is number of trials until first success, right? And if you have negative binomial, if you remember, we talked about negative binomial distribution where we have k successes, and between every successes, consecutive successes, the number of trials between 2 successes was the geometric variable. So if you have these number of trials, instead of measuring the number of trials you make, if you measure time, that becomes exponential. So it's like exponential is a continuous case of geometric distribution where we're not counting trials, but we're measuring time, which can be continuous and real value. This is what exponential distribution is. And we're going to see something really interesting in exponential distribution, which is also true actually for geometric. We haven't looked at the geometric distribution and discussed it in that. I think maybe it was at the end of the end chapter exercises. It's called the memoryless property, which is also known as the gambler's dilemma. If you've ever heard of this term, gambler's dilemma, meaning that, for example, if you're a gambler playing in front of a slot machine, for example, if you have seen that, exactly, it's also zarın hafızası yoktur in Turkish. Also, it's also not zarın, but it's also the slot machine doesn't have a memory either. It's like the gambler's dilemma is this. If a gambler did not win for a certain period of time, the gambler is going to always think that, okay, if I know that I haven't won in this last 1 hour, so it means that my probability of winning in the next few tries is high, right? But intuitively, he may think like that, but this dilemma shows that the knowledge, this conditional probability that an event did not occur in the first t minutes, does not give you any additional information. So the waiting time to the next event, the probability of waiting at least X minutes is always the same. The probability does not change. Like, for example, you have wait for a day, you haven't won anything, you know that. What is the probability that you will win in the next 5 minutes? Is exactly the same probability that if you weren't given this information. If you started just at the beginning, knowing nothing, what is the probability that the time to next success is 5 minutes? Is exactly the same as saying I have waited 1 day. What is the probability that I will win in the next 5 minutes? They have the exact same probability. So this is a really nice, interesting property of exponential distribution. And this is also geometric distribution. This also is the same thing. I mean, given that you have already performed certain number of trials without success, what is the probability that the success is going to occur in this many trials is exactly equal to the probability, unconditional probability to observe the success in that many trials. Yeah, so another thing is sunk costs should be disregarded. Your loss, what you have done, you weren't successful in the first certain amount of time, should be disregarded. That's also another thing. This is also known as gambler's dilemma, and both exponential distribution and geometric distribution has this property, and no other distribution has this. So it's like it means that it's really interesting if you think about the exponential distribution. And after that, I'm going to have a break. Let's get a new blank page. It means if you think about exponential distribution, it has a shape that is like this. What it's saying is that the property is this: the probability under the curve in the first t minutes like this is equal to, if you focus now on the right hand side of the figure and try to find the area under the curve, average over this ratio here, it's the same. So let me give names to these areas. For example, if this, let me use a different color pen. For example, if this area is A, if this area is B, and if this area is C, the memoryless property says that if this is the same amount of time, if this is amount t and this is also amount t, and we are asking the question at this point, we haven't observed anything until t. So the probability that the success is going to occur in the next t, given that this was not successful, actually is simply b over c, right? Since this is a conditional probability, we know that it didn't occur here. The probability that it's going to occur, not b over c, b over b plus c. Okay, these are the individual areas like this. So b over b plus c is the probability that we are going to observe a success after this point here, knowing that no success occurred here. This is actually equal to a over a plus b plus c, which is 1. Okay, so this part is 1 because since it's a probability density function, a plus b plus c should be equal to 1. So it's like every time you're looking at if you look at a snapshot after this point, this will also look like an exponential. So it's like a fractal. You zoom in, after a certain point, this part is going to look exactly like its shape is going to look exactly like the shape that you see here as you zoom in those small portions. So the ratio is always going to be the same. So this is called the memoryless property. We are going to talk about this in more detail. Now let's have a break. I'm going to stop sharing my screen and stop the recording.